covariance. So the covariance is, remember, the expected value for two random variables, the expected value of x minus expected value multiplied by y minus expected value. So this is kind of centering it around the center of mass, saying how they vary with each other. If x gets big and does y also get big, that would point to a positive covariance. And negative would be if as x gets big, y gets small. What this number maybe is hard to interpret. Is this a large covariance? Is it a small one? The correlation is a way to make the number in some ways more understandable, independent of the scale of the number, and it divides by the standard deviation of x and the standard deviation of y. Right? This is kind of squared term, and you're multiplying by two terms each with you're dividing by two terms each in the same units of the data. So this term does not have any units, and the nice thing about it is it will be between -1 and +1. So if you know it's very close to plus 1.95, that means it's a very high correlation. They're very correlated. And close to -1 means they're very uncorrelated. It means if one varies, you know the other one is going to be, if one's increased, the other one's going to be decreased. So a common kind of confusion about this has to do with independence. So if you have two random variables, x and y, so the independence, x and y, implies that the covariance of x and y equals 0, which implies the correlation also has to be equal to 0. Okay, this does not go the other way around. Right? Covariance equal to 0 does not imply that these are independent of each other. Okay, and a simple example of this is that, let's say that x is from the uniform distribution between -1 and 1. Let's just say it's a simple distribution. That means it's PDF everywhere between -1 and 1 is going to be 1/2, and it's 0 everywhere else. And then we'll say that y is going to be exactly equal to, say, x squared. Okay? These are very dependent on each other. You know, in the sense that's kind of the common English word of dependence. If you know the value of x, then the value of y, it depends exactly on it. You know, if you know that this value, you know this one exactly. So the plot of these would look like, you know, you have an x value here and y value here. Then the only place you actually see stuff here is going to look like this, right? It's actually a function. Okay, but the covariance of this is still going to be 0. Okay, so basically for everything on the right side of, and this line between -1 and 1, everything on the right side will essentially cancel out with something on the left side. So half of it varies together, and half of it varies inversely, and they cancel each other out. So the covariance is exactly 0, but they're not independent of each other. Okay. So filling in some details from on Monday. Okay, so the other kind of news, the homework one is officially posted on the website. Has anyone not tried and not been able to find homework one yet? Okay, so it should be, it's linked off of Canvas, it should be, and linked off the website. It's due in 2 weeks, I think. Is that right? No, it's due on September 11th, which is, yeah, so that's in 2 weeks. You should be able to do most of it. Question 3 should, you maybe can start thinking about after the lecture today. We'll see more stuff on lecture a week from now. There's no class on Monday. That will kind of go over how to attack those sort of problems in some more detail. All right, so, okay. So today's topic is going to be so Bayes' rule. Okay, just a note about the name. Bayes, Thomas Bayes was a person, and so it's his rule. The apostrophe goes after that S. Okay, that's not a mistake. So Bayes' rule is just a simple probability fact about two random variables. So I have two random variables, and I'll use M and D, and we'll see why M and D will make sense as random variables. And it's that the probability that so given D, I can rewrite this as the probability of D given M times the probability of M divided by the probability of D. Okay, so hopefully you've seen it, so you've seen Bayes' rule before. So in this lecture, we'll hopefully, well, I mean, maybe you've seen it used this way before, but we'll start using it to do actual data analysis. Okay, so hopefully, so who's not seen Bayes' rule before? Okay, good. So just for completeness, you know, I just want to just prove that it's true. You can derive probability of model intersect data is equal to the probability of the model, or sorry, of M intersect D of M given D divide times the probability of D. This is from the definition of the conditional probability, but I've instead of dividing by probability of D, I've moved it over onto the right-hand side. I can similarly write M intersect D is equal to the probability of D intersect M, right? So this is doesn't matter. The intersection is going to be symmetric, and then I can apply the same trick here times the probability of M. Okay. So now these two are the same, so I can write probability of M given D is times the probability of D is equal to the probability of D given M times the probability of M. Right? And so then to get the final expression here, I just need to take this guy and divide it through. Okay, so just by doing algebra, you can derive this rule. It's nothing magical. It comes from the definition of probability of intersection and the probability of conditional random variables. Okay, so you may have heard about this controversy between Bayesian statistics and like frequentist statistics. This is not a controversy about the like whether this theorem is true or not, right? It's kind of a choice of how to go about like modeling data and to explain the significance of various things, right? A frequentist point of view will have a much more rigid model of the data. They'll make assumptions in terms of a model one way and try and report the significance based on this model, where Bayesian will more try and talk about the probability of different models. be significant or it's not significant. Okay, and kind of over the years, you know, this maybe was an issue, I don't know, 15, 20 years ago. Most of this class will not really look much at frequentist or Bayesian statistics. You know, a lot of the concepts, the mathematics underlying the ideas are very similar, and we'll see some Bayesian justification for some of the analysis we do. But the analysis of evaluating, kind of trying to do learning or data analysis or building models or evaluating which model is good will be from a more of a, what I call a cross-validation point of view, which will kind of not be fall entirely into either of these camps. We'll motivate it somewhat from a Bayesian point of view, but it probably arose from the frequentist side of statistics. Okay. Okay, so let's just, you know, this starting from this lecture, the pace will be going slightly slower. I guess Bayes' rule itself should be reviewed, but you know, we'll start introducing what I believe will probably be new material for new ways of thinking of things for most of you. Okay, and so let's look at this. Let's just check Bayes' rule, and let's say we have random variable m and d, and they can either each take on a value of 0 and 1. Okay, so then we can write down a probability table. M equals 1, m equals 0, d equals 0, d equals 1. Okay, and I can fill in a probability table, 0.25, 0.5, 0.2, 0.05, right? And everything here looks good. These should all add up to 1. And so now, if Bayes' rule is true, what we should have is that the probability that the model, say, 1 is true. So if I write probability of m, that means probability takes on value 1, right? Given that the data is true, right? So the probability of model, so I'm using m and d as random variables, as m will represent model and d will represent data. Sorry, I'm meant to say that after this, but true should be equal to the probability of m and d this should be equal to the probability that d given m times the probability of d of m divided by the probability that d was true. Okay, and so we can drive both the left-hand side and the right-hand side. Probability of m given d is going to be equal to, so given that, so the probability of m and d is going to be, switch this up a little bit from my notes, but okay, is 0.2, 0.2 is the intersection divided by the probability that d is true, so that's the sum of these two, 0.25, right? And so this is equal to 4/5, and then let's drive the other side. Okay, so the probability that d is true given that m is true, right? So that's again going to be 0.2 divided by 0.45 times the probability that m is true. That's going to be 0.45 divided by the probability D is true, it's going to be 0.25, right? And so these cancel out, so 0.2, 0.25, which is also 4/5. Okay, so, in this example, it was true.
So like when you're writing it out, when you say the probability of m given b, are you referring that m equals, you're just referring to m equals 1 and b equals 1?
Yeah.
Oh, okay.
Yeah. Right. So think of this as binary true false. You're all computer scientists, right? So yeah. But I could set it to be a particular event, and that'd be fine as well. I could do it for m equals 0 or something else, but in this case, it's m equals 1 is true. So all right, it was true in this case, and the point of Bayes' rule is supposed to be that some way this right hand side. And in this example with the truth table, okay, the left hand side was easier to compute, right? This calculation was easier, right? So I haven't really done anything interesting. Okay, so if you've just seen this before and you've done the calculations, this does not seem very interesting. Okay, so let me start with a slightly longer example, but that will hopefully show how this is going to be interesting. Okay, so now, okay, the story is that I bought a new car. This isn't a true story, as opposed to the one with the dirty clothes, which that was actually true. Okay, so they spell shield. I bought a car and the windshield was cracked. Okay, I drove off the lot, the windshield was cracked, and so I have this random variable that my observation that the windshield was cracked, it's 1 in, so in my case it's 1. Okay, so I want to investigate what's going on. Is this an unlikely event? Who can I blame? Or who's the most likely person to blame? Okay, so I found that the car I bought was it was manufactured at one of 3 different factories, right? Most cars are not all built, it might not all be built in one factory, but maybe, or the windshield came from one of 3 factories around the country. And I'll call these factories A, B, and C. Okay, and I want to know which one of these manufactured sites was most likely to have made the windshield, which was broken, so I can know where I should start complaining. All right, but I looked up some statistics, and I find that the probability of a windshield being made in each of the factories is so it's not uniform, right? So factory A might be closer to Utah than factory B, right? So they're more likely to get it from A, and so the probability of A was say 0.5. The probability of B equals 0.3, and the probability of C equals 0.2, right? So 50%, 30%, 20% of these factors. So if I just look at this, I'd say, well, it's most likely it's going to be from A. Okay, but then I looked up some statistics, stats on the factories, and I see that some of the factories have higher rates of cracked windshields than others, right? And I've made these percentages probably like absurdly large so that the numbers are more easy to think about. But so at probability of getting a windshield that's cracked is only happens 1% of the time. Factory B, it's a problem and it's 10% of the time. At factory C, it's not so bad and it's 2% of the time. Still worse than A. Okay, so how can I combine these together to kind of understand which factory was most likely to have been the source of my cracked windshield? Okay. Yep, question?
Are you asking us to use the tree chart?
So you could do this through a tree chart. There are ways of doing it. I'm going to show it through Bayes' rule, right? Okay. So maybe you've seen something like this before, but this will be kind of the warm up towards data analysis. We'll do another example towards the end of the lecture where I give you some data points and we'll actually calculate probabilities of kind of a more abstract problem. Okay. Okay, so first of all, I need to turn this into into probabilities. So this turns into the probability that given that the windshield was cracked, that it came from A. No, so what we would like to find is the probability that it was A given that the windshield was cracked. Okay, so but I want these stats to mean that the probability, given that the windshield came from factory A, the probability that it is cracked is 1%. So this is 0.1. Okay, so given that it came from factory A, the probability it's cracked, this is something I can look at. So the probability that the windshield is cracked, given that it came from factory B, is 0.1, and the probability that the windshield was cracked, given it came from factory C, is 0.2. Okay? Okay, so now I can put this together. What I would like to calculate is the probability that it came from factory A, given that my windshield is cracked. I know my windshield is cracked. What's the probability it came from factory A? Okay. So this is going to be, so the probability of the wind, so I can use Bayes' rule. Okay, so I can write it as the probability windshield was cracked given it came from A, which I can look up these statistics. The probability came from A, divided by the probability that the windshield was cracked. Okay, and I can, so in this case, I can write down these numbers. This is 0.01. The probability that it came from A is going to be 0.5, and that divided by the probability that the windshield was cracked. So sometimes people say that this, maybe I know that it's cracked, so it has to be 1. That's kind of not the right way of thinking about it. This is kind of the probability that any windshield I see is cracked is what this should be. And I don't know what that value is yet. Turns out you can calculate it from this information, but it turns out we won't need to do that. Okay, okay, so I'm going to leave the answer like, so this will be 0.005 divided by the probability of W. Okay. And I can do the same thing for the probability D given W, which is probability the windshield is cracked given from B, probability B divided by probability W, which is going to be now it's 0.1 times 0.3 divided by probability W. This is now 0.03. And then the same thing for that it came from factory C, and that's going to be 0. This is 0.02. This is 0.2. Okay, good. So now I know that I can look at the probability it came from each of these factories given that it was cracked, and I can say that, and I can compare these different probabilities to each other. They're all divided by some unknown value here. Well, you know, I know these have to sum up for 1, so I can solve for it. But what's most interesting is that I can figure out which one is the largest, right? So this one is the largest. So the largest probability of where the windshield came from, given it was cracked, was B. Okay, and this allowed me to combine together this different information about the statistics of each factory with where they came from. Okay, and so this is the sort of thing that Bayes' rule is useful for. Okay, not so much for those kind of doing some algebra on those probability tables, but in kind of combining together different sources of data. Okay, and I didn't need to know what this concept was, and this will be more generally true. In this case, I know there are only 3 different cases, and I could set them equal to 1, the sum of them equal 1, and I could solve for it. But in some cases, there's actually going to be like an infinite number of possible choices, and I'm not going to be able to either integrate or to add up all the different things, or that would cost too much. I just want to find the maximum, and so I don't actually need to calculate this concept. I just need to find which one is the largest. So, okay. So this is kind of a specific example of where it's useful. But as I've been using these M and D as these random variables, the more general sort of use case is going to be where M is representing the space of these of models, and D is going to represent the data I've observed. So I'm going to have random variables M, and this is going to represent the model of my data, and D is going to be the actual data. So I've observed some data, and so that's going to be given, right? So I want to then calculate the probability of a model given that I've seen some data, right? So I've observed this data. This is now known to me what value this takes on. And I want to say, what is the most highest probability model that represents the data somewhere? Okay, so this is kind of where it meets data analysis. Okay, and this kind of and so there's a maximum a posteriori one says this, they say a map estimate. Okay, a map estimate is going to be the model which maximizes this, right? So it was, in this case, the models were the different factories, and the highest probability factory, given the data I saw, my windshield was cracked, was B. Okay, so there's basically, I'm going to think of having some model which is going to be some element of some space of models. Okay, this is going to be a space of models. Okay, yep.
Are we reducing that space of models through like other means, or like are we reducing this model for this procedure, or does this procedure produce the model itself?
Yes, actually. So we're going to need to define the space of models, so we produce it. But the procedure we're going to describe is actually going to produce the model which maximizes this, which is what we want. Okay, so we have to describe the space of models, and that will restrict essentially our possible space. Okay, and so what we want to find is M star, which is going to be, I'll write down this notation, and if you haven't seen it before, I'll explain it. Okay, so we want to find M star, which is going to be the R max of this function, probability of the model given this data that we've seen. Okay, so if you haven't seen arg, so who's seen this arg max expression before? Who's not seen this? Okay, so you've probably seen a max. You've probably seen a max operator, right? You have a set that returns the value that maximizes any set, right? So I can have so let's give an example. I'm going to have a set S, which is going to be 1, 3, 6, okay? And then I'm going to have a function, f of x is going to be x times 2, okay? Doesn't matter so much. The max element of the set S over the function f of x, okay? This is going to return me the maximum value this function can take. Okay, so this is going to be 6 times 2. This is 12. The arg max f of x is going to return instead 6. It's actually going to be the element of the set. Okay, this set does not need to actually be numbers. It can be like factories, right? Right? It could be like I'm processing these text documents, and I'm saying which text document is most likely to be a relevant search query for some keyword. The argmax will return the text document, where the max might return the similarity score. Right? So the argmax returns the argument of the set, where the max returns the function value. Okay, so these are common notation, and it's important that we are distinguishing here between the argmax and the max. This means I want to return the model, which maximizes something, like the factory over here, but I don't actually need to produce this value. Right? Just like I didn't need to know how to divide through by probability of W, if I wanted the value, I would have had to calculate that. But I just care about which model maximizes it, so I don't actually need to calculate the value. I just need something which is the argument which maximizes it. Okay? So this distinction is important, and it'll allow us to do calculations of a lot easier calculations. there's a whole field of like computational Bayesian statistics where they try and do things like actually calculate the value, but they often can't calculate this, so like this denominator. So there are all these kind of randomized algorithms that you do to try and estimate it in order to try and estimate these statistics. But it's a lot easier if you don't need to estimate the value, you just try and maximize this, maximize the arguments. Okay, and so this means, so I can write this as this is the arg max of the model of probability of the data given the model times the probability of the model divided by the probability of data. Okay, and the important step here is that this is the same as the arg max of the probability of the data given the model times the probability of the model. Okay, so this, I do not need to divide through by the probability of the data because for every model that's going to be the same. Okay, so yeah.
So M star is the math estimate?
Yeah, so M star is the math estimate. That is the return thing argmax. So often a common notation is that when I return an argmax, or the argmax, maybe I don't have a function to return it, but just mathematically I will denote with the star. Okay. So the stars usually refers to the max. Okay. So the argmax is the same whether I include this denominator or not, because it's going to be the this term does not change for every model. So I just need to deal with the product of these two parts. Okay, and this was the same over here. You know, I carried it through, but I didn't. I could have, if I knew I just wanted the map estimate, then I could have dropped it from this notation, and this would have been a little bit easier to read. Okay, you can carry it through, but it just makes it harder to read. That's my argument of why that's hard to do. Not like anything. All right. Okay. So this is kind of a very simplistic, discrete example of models. These kind of three factories, but other sort of models we'll see in this course. So something I think we'll get to. I think we'll get to soon in this lecture is where M is going to be a single point in the space of the real numbers. Okay, so we'll go through an example in this lecture today where we'll look at some actual data, I think 5 data points, and we'll estimate a single point in the space of real numbers. Okay, so but you know, the other parts are going to be just kind of more complex forms of this. Okay, in general, it can be a point in d-dimensional space, but we'll wait until we have reviewed the linear algebra to talk about that stuff. But it turns out the calculations will be exactly the same. Okay, so it could also be that M is a line, and I want to, and in this case, I want to fit to the y values of some data points. Okay, so this is the problem of linear regression. Okay, so when here my M is going to be a line, and I want to somehow find the most likely line with respect to looking at the y coordinates of data, and this will be the problem of linear regression. We'll spend a section on this. We won't so much talk about it from this Bayes perspective, but it'll follow the analysis is just a more complicated version of the single points. So if M is going to be a set of k points in RD, so I have a d-dimensional space, d-dimensional real space, and I want k points, and I want all the data points to be close to one of them. Okay? So then this will be the clustering problem. Okay, now the model is a set of k points here, and this is clustering. Where did my eraser go? Okay. So you see my eraser. Okay.
Your little rag eraser?
No,
Your paper towel eraser?
no, I upgraded. I upgraded the last lecture, and then it's gone. So, all right, back to, and I didn't bring my paper towel, so I'm using my arm. Okay, this will. Yeah,
Don't be blue.
Solve the mark of a professor on me. Okay. Then we'll also look at the case where M is going to be a k-dimensional subspace in RD, where k is going to be, say, less than d, and I want to fit, say, n points in RD. So I want these endpoints to be close to this the subspace that best represents those endpoints. This is going to be the PCA problem for so dimensionality reduction. Okay, so I want to start with the d-dimensional space reduced to k-dimensional that best fits the data. This is again just going to be kind of a more complicated extension of the single point problem. And then finally, so M will be a half space, or let's call this a hyperplane, okay, which divides two classes of data. Okay, so I have two types of data, positive labeled, negative labeled, and I want to find a hyperplane that is separating these as best possible. Right? So the guess of some dividing line that a data point is likely to be labeled one way on one side and unlikely the other way, this is the classification problem. Okay? And all of these, we will effectively formulate them as we're trying to find the single model which best fits the data. Yeah. Oh, so sure. Thanks. Okay. So let's So I want to go through one example of this, but I need one more kind of trick. Let me go through one more general trick and notation before we start this. There should be video evidence of where my eraser is. It's a good thing about recording. I was erasing stuff earlier, right? So yeah, no one knows where it went. There must be gnomes in this room or something. So okay. What?
Started over here. You got
talk about something called a log likelihood. Okay, so this will be kind of a simple transformation that again kind of will rely on that we're using this argmax estimator. And that'll make calculations both easier from a kind of actually doing them in practice standpoint, and also numerics and stuff. So much better. And so the idea is that we're going to write a what we're going to instead so in some cases, and I'll talk about this if we go fast maybe today, but we're going to write down the probability of model given the data. Remember, we can say that this is and if I'm doing the R max M, okay, so if I'm doing this, it's going to be equal to the R max, okay, of the probability of the data, so given the model times the probability of the model. And so often what you do is you might assume that I don't know anything about the model, so let's just for now, and we'll come back to this, but I'm going to assume that the probability of the model is going to be uniform. Okay, so I'm not going to assume anything about the model. One model is more likely than another. Right? In the windshield example case, I knew something about which factor was more likely to deliver windshields here. But let's say I don't know anything about it. So I'm going to assume it's uniform. And what that means is then I can essentially drop this term as well. Okay. If that's the case, then the argmax is going to be the same. Okay, so then if that's the case, I can actually say the probability of the model given the data has the same optimum of the probability of the data, so given the model. Okay, if I don't assume this term, which will be called the prior, if I don't assume anything about the prior, then I can set this, and this is called the likelihood. Okay, so this is the likelihood of the model.
Uniform probability.
The what?
Something about uniform probability.
Yeah, so an example with the windshields would have been if each of those were 1/3. I could have dropped it. For continuous models, like the space of a single point in the real line, it's a little bit trickier because the real line is infinite, right? So I have to assume that they're all equally likely. So I can't even write down a value so it integrates to 1. So you kind of have to do some like gymnastics within the calculus to get it formally correct. But the point is, like, if you don't assume anything about the model, you can just drop this term. You could also say, well, the model, the single point needs to be between -100 and +100. I know it's not outside there. Then I can assign it. I can give it a PDF. That's like 1/200, and that's fine. So it's the same for everywhere there. And if it falls outside there, I have to do some bad cases. So there's. All right. So the trick is going to be that instead of M star, right, the maximum here, I'm going to also be able to write that M star is equal to the R max of M of log of the probability of the model given the data. Okay? I want to do a log transform here, and that's name is going to be arg max of log of the probability of the data given the model. Okay, now this term is called the log likelihood. Okay, and so this log likelihood will be easier to work with, it turns out. Okay, so this is the log likelihood, and this works because a probability is always going to be greater or equal than 0, and on the range greater than 0, log is going to be monotonic. Okay, so from 0 to infinity, we'll actually only need to go up to 1. The log operator looks like this. Right, so for any value here, the larger the probability, the larger the log of the probability. This is log of x. Right, so it's a monotonic operator. Okay, so the same point is the same maximum. Right, so there's lots of different models that can sit, say, along here. Let's say it's discrete. Each is a data point. The log of that probability maps the values, and the one which is maximum on here is the same one. This is the maximum probability, this is the maximum log probability. They're the same, they refer to the same model. Okay, so I'm just mapping to a different function. It's a monotonically increasing function between 0 and 1, so this is fine to do. There's a technicality that log of 0 is not necessarily well defined. We'll pretend it's minus infinity, and then it's fine. Oh, is this actually log is not positive? This is it's negative. It goes down to infinity. I didn't draw this picture, but so log is actually goes like this, right? It increases that much. Okay, so a probability is going to be a negative value. The log of the probability will give me a negative value, but it's monotonic, so it's okay. It doesn't matter. So sometimes you write down the negative log likelihood, and that's because it's easier to think about positive values, and then you want to minimize the negative log likelihood instead of maximizing the log likelihood. Okay.
Could you explain again why we're taking long?
We'll see an example why we're taking long. Okay, the cool thing about log is that so we're going to look at a bunch of assumed data points are going to be independent, and then we're going to get probabilities, and because they're independent, we can multiply those probabilities. And so a log has the property that log of A times B is equal to log of A plus log of B. Okay, so if I'm multiplying a bunch of probabilities together inside of here, then it becomes a sum. I can write now as a sum. And the sums are going to be easier to think about, easier to work about. Easier to work with. Okay? Also, the base of the log does not matter. The base of log does not matter. That's because log base b of x is equal to log, what is it, base, I don't know, let's say base uppercase b of x divided by log uppercase b of lowercase b. Right, so the two b's are constant factors. So this is a constant factor, so I can switch the base of the log and I get the same maximum point. Right, this doesn't change the argmax. It changes the max, but not the argmax. Right, so I can choose any base of the log I want. And so for the example we'll use actually the natural log. And we'll see why. Yeah.
So this scales all the data down and kind of like destroys the usefulness of the data produced by like probability things. We still get the right model.
yeah, we'll still get the right model. Turns out, and here, this will hopefully be clear after the example. So I can use the natural log. It's gonna be kind of like hopefully this is like a little magical if you haven't seen this before. Okay, so let's set this example up. Okay, so I'm going to have some data set. Data D is going to be, and I'm going to estimate a single point estimator. And so I'm going to have a set of points which are going to have values 1, 3, 12, 5, and 9. Okay, so this is, think of x1, x2, x3, x4, and x5. Okay, so I'm going to have 5 data points. And so I'm going to, and I want to find the space of the models is going to be the real line. So I want to find a single point estimator of the model. So M is going to be an element of the real line here. Later on, we won't use uppercase M for this, but for now, just so everything is big M and big D. We'll keep it that way. Okay, and now we're going to assume that that this data is generated from yeah.
Find a set of all models of what type of data?
Yeah. So I'll explain. So the actual model, which will kind of, when I say here, I want think of the model as being kind of a geometric object. That's how I think about it. It should, and for the rest of the semester, we'll kind of ignore, kind of brush past essentially or under the rug there's a noise generation part of it, which is kind of implicit. I'll write this down explicitly now. Yeah, so we're going to assume now that this data, each data point was, that each xi was generated, so in the, so pendantly from some, from a model which is going to be it's going to be a normal distribution. For a normal distribution with a standard deviation of 2, right? So this is a normal, which is going to have a mean value m and a standard deviation of 2. And so we're going to assume that it's generated from this data was generated at each point independently from this model, okay, from this noise model. Okay, and so we assume we know the standard deviation. It turns out that it won't matter what the standard deviation is, but for now, assume this is known. Yep.
Sorry, does that M by the mean correspond to the model M or the mean M?
Yeah, so in this case, we'll use it as just a single scalar value, right? So this is the model,
Okay, model
right? This is the unknown model. We're going to put a probability over the choices of this M.
Okay, thank you.
Yep. Okay. So that means that, in particular, if you remember that I talked a little bit about this normal distribution, right? And this was kind of in general with the standard deviation. This was going to be 1 over sigma to pi e to the negative m minus, so this is added value x minus x squared divided by 2 sigma squared. Okay, so, and in our case where sigma equals 2, this is going to give us, and I'm just going to write this as a function g of x, okay, so like, just for Gaussian, which is going to be 1 over square root of 8 pi, at x, e to the negative x, I'll write this, it's easier to write this as x to x. Sometimes writing exponents, it's hard to see where the exponent starts and ends, so exp refers to this. Okay, and so this will be x of minus m minus x squared divided by 8. Okay, so this is going to be, and this is going to be equal to the model, the probability of the model given that the data is equal to x. So if the data was just a single data point x, this would be the probability of the model. Sorry, no, this backwards. So this is the probability of the data. Yeah, so this is a PDF. So it's not quite a probability, it's a PDF, but essentially it's, and this notation of using probability is a little weird when you have PDFs, but for now, pretend it's a probability of the data of the probability of x given this model. So if m is fixed, if I know what m is, I can evaluate the probability of seeing this data point. Right, so if I know the model, let's say the value of m is 7, and I knew the data was generated with noise, and the probability of seeing any given data point, or its PDF technically, is going to be this. That's the probability of seeing x given this model. Okay, so this is common, that given a model and given which could be an object like a mean and a way of generating noise, which is usually implicitly is Gaussian or normal distribution, I can write down the probability of seeing any given data point given this model. Yeah.
That's assuming that the model is accurate, right? Or
sure, yeah. It's assuming the model is accurate. And this is often, and we'll see this, and yeah, so there's, this is an assumption that we have normal noise. This is the most common assumption that shows up, and we'll see it's going to correspond to a nice optimization problem, which will be easy to solve. One of the reasons that this model is chosen. Yeah.
So later our first step will be to like construct this basic model and then apply this technique and then find the best model.
So yeah, so we'll actually do this. We'll actually do this right now. Okay, so in this case, I assume the model was basically data was generated independently of Gaussian noise, and I just need to pick a one-point representation, basically the mean. Right, so I'm assuming the space of models is means, and that's what I'm solving for. And there's an implicit Gaussian noise model in there. This Gaussian noise model is going to be implicit in regression, the clustering we do, and in the dimensionality reduction we do. It's not the right thing to use in classification. We'll actually look at that noise model. Okay, but this is kind of often the right model of noise. Okay, or at least it corresponds with the most common formulations, which have nice algorithms. Okay. Good. So this is the probability of seeing one data point given this model. So then the probability of seeing an entire data set D, okay, remember D is going to be the set of these 5 data points, is going to be the product. If you've ever, like an uppercase pi is roughly a product. There's, like in LaTeX, there's slightly different symbols. In LaTeX, this is prod not, which is not equal to uppercase pi. These are slightly different inside LaTeX, but it's a product over the data points xi in the data set. Because they're independent, that means their probabilities, I can multiply them together of the probability of seeing xi given m. I can say what's the probability of each of them, and then I can multiply those together. The joint probability is the product of the probabilities because of independence assumption. Okay? And this is equal to the product of xi and d, and we'll just use this g of x, which is this exponential. Okay, so now I can write down this product, this P of D given M, and if I made this assumption that the models are uniform likely, then this is sufficient to find the maximum likelihood estimate, the maximum model given the data, and those are the same. I can find the model which maximizes this is going to be the model I want. Okay, and it turns out it'll be better to look at the log, and I'll use the natural log of the probability of the data given the model equals the product xi and d of the natural log of the product of g of x, which is going to be equal to the sum of x of I and d of the natural log of g of x. Okay? There's this cool trick with logs that I can bring a product, can bring that outside the log, and it turns into a sum. It's a special property with logs. That's, you know, when I first learned about logs, I'm like, these things are kind of don't make any sense to me. And then I went into computer science where they show up in binary search and in all of this stuff, right? So, all right. Okay, these logs are, so, okay, so now let's try and write down what's going on. Okay, so this of the probability of the data given the model, and let's say, okay, so this is going to be equal to, let's actually write this down. It's going to be equal to now the sum, the xi and d of the natural log, and now let's write down what this g function is. It's going to be 1 over square root of 8 pi x to negative mx squared over 8. Okay, and now this is again a product, so I can break this up into two terms. So it's going to be xi and d, and now the first term, let's move this term, this coefficient outside. The first term is going to be the natural log of x 8 plus the, now this term is constant for every one of the data points. So instead of a sum, I can just count how many things are in the data set. This is a cardinality of the set. In this case, it's 5, right? And then it's going to be the natural log of 1 over square root of 8 pi. And because we, okay, so we can do two things now. First, I have a natural log of an exponent with the base e, which means these cancel each other out. Right, so this is just going to be minus, okay, minus the sum of the squared differences from m. This is xi. And this term is the same for every model I take. It doesn't depend on the model, so it's going to be some constant, and I can ignore it. Okay, in fact, this 8 is going to be the same everywhere as 2. So this is going to be proportional to of, let's say, right? And there's going to be divided by C1 plus C2, right? So there are these extra constants that I don't worry about, right? Because multiplying by something or adding something does not change this argument. Okay, so what this means is that the arg max m star of m in the space of the models, and in this case is the space of the real numbers, okay, of the natural log of the probability of d given m. This is going to be equal to the arg min, changing from a max to a min of m in the space of the reals of the sum of xi of over all the data points of m minus xi squared. So I've gotten rid of this minus sign as well by changing from a max to a min. Okay, so the maximum log likelihood, given that I have some 5 or n data points selected from a single point with normal noise, is going to be the point that minimizes the sum of the squared distances. Okay, so this looks much simpler, right? So the arg min, right, by doing the arg min in this log transform and some calculus, it's just the sum of the squared distances. The point that minimizes the sum of the squared distances, right? So I've got points on the line, I've got 1, I've got 3, there's 5, there's 9, and there's 12, and I want to find the single point, m, which minimizes the sum of these squared distances. Okay, so some point m, probably right here. I want to take all these distances and square them and add those up and minimize that cost function. This cost function, where you want to find something that minimizes the sum of the squared distances, is going to show, it's going to be kind of the thing we analyze for most of the rest of the course, until the last couple lectures when we deviate with classification. We'll change it a little bit. Okay, and so it's motivated partially from this Bayesian model, assuming Gaussian. Okay, why else is it motivated? Yep.
So what happened to your rate of time when you transform from R max to R min? You just put it kind of into a constant.
It's important I switch from max to min because that flips the negative sign.
Okay.
I did those. Those are linked together. I can't do just one of them. I had to do both of those. By going from max to min, basically, think of there's some function, and I wanted to find the maximum of this function, and it's the same thing as finding the minimum of the negative of that function. Like if this is the 0 line, then the minimum of the negative of it is the same as the maximum of the original function. They have the same value m star. So it's an important point. I couldn't just switch from max to min. I had to also do the negative sign. But I had this annoying negative sign anyways, right? And usually these log likelihoods were actually usually negative values. So it's usually you look at the negative log likelihood as well. Okay. So what's the other reason that we often focus on these sum of squared distances? The other reason is that there's a simple algorithm. Okay? Does anyone know the closed form solution for this? Okay, it turns out that this is equal to size of B. Just the average. Turns out the average, you add up all the values and you divide by the number, the average of them is the closed form solution to the arg min for the sum of the squared distances. It's not the minimum, it's not the argument for the sum of the distances. This is actually a common misconception, which is like found its way into like the, I think it showed up in the laws of the U.S. accidentally, because someone assumed that was the average was the sum of the distances, but there's something about the average point in the United States based on either land volume or population that showed up in a law, and they meant it to be the sum of the distances, but they wrote it as, or, I don't know. But so the average, it turns out, is what minimizes this. And this is the simplest thing that you can do to build a model. I want to build a single, if you went back here and you said, I had data points I thought were drawn from some distribution independently, how to estimate the center of that distribution, you would probably take their average. And it turns out if you assume Gaussian noise, then that is the right thing to do. Okay? It doesn't matter what the standard deviation was, because at this step right here, this is only the standard deviation showed up here, which was a constant, it didn't matter, and it showed up here, which was a constant, it didn't matter. So it didn't matter what standard deviation I assumed. Okay, that disappears, right? But the, you know, if I assume Gaussian noise, it turns out the right answer is the average, and this has a simple algorithm to compute. And the similar will be true with linear regression and with clustering and with PCA. Both of those, when I set up a model which implicitly is Gaussian noise, there's going to be an algorithm which effectively will minimize the sum of the squared errors. Right? This is the sum of the squared errors from the model. If I'm minimizing that, I'm implicitly assuming Gaussian noise. And that comes from this Bayesian derivation. The average of D?
Oh no, and the blue thing. So on the left side?
Yeah.
On the other side?
Oh, here.
Other side of the other side of, yeah, there. So where did the D come out?
This one.
Yeah.
Yeah, so so I had a sum, and I had this sum over, I could have summed over D terms with this term, but it doesn't depend on xi or on m. So it's an absolute constant. Right? And I multiply it by the number of data points, but that's fixed.
Okay.
So I just fold this all into a single constant. Yep. So this is pretty cool. Yeah? All right. Okay, so I think we'll stop here. We'll kind of review this, and we'll do a little bit more and some terminology and go through some more examples on how to actually, some examples of using this a week from today. And the third homework question will be kind of doing something like this. And if it's still confusing, hopefully you'll see more in the next lecture. So it'll be a bit easier.